All right, so we continue with the last talk of the afternoon. As always, a great pleasure to introduce a great scientist, humanitarian, and a friend of mine for 20 years.
So this is well, it's the last talk, and it's a few of us, and
Yeah,
we are very
take it easy.
So I'll really give an impressionistic view of what I want to say. 2 or 3 areas. This, of course, joint work with Mill. After being so many months in Sofia, I should know that I should be not good at them. And Doha and Kyongso. But of course, the 2 pronunciations are wrong. The 2 pronunciations are wrong.
Of course, also,
But it's what a challenge for me.
No. French one, you're doing well.
Well, he doesn't agree. So it's really a challenge, sorry. So anyway, it's about non-Kähler geometry, of course. It's in part about LVM manifolds, but in part what they inspired more generally, and how think of them as a laboratory to think about some ideas. And it doesn't work. How do you do it? It won't work, so.
Yeah, it does. You just have to turn it on.
Of course. Thank you.
Yeah.
So again, we already Laura already talked about this during his talk. You get these manifolds interested in Mexico, the CINVESTAV of the Americas, interested in Mexico by Santiago and Alberto in '97. It's going to be 30 years next year. So it's going to be 30 years next year. And Laura generalized them importantly in 2000, and then there was a small further generalization in 2001 by Bosio. And so we have these input vectors.
Wait, so is there some younger mathematician with the Medrano's family name?
That's right, Lucia.
Okay.
Lucia in tropical geometry.
Yes.
She's a good tropical geometer. So, in any case, so this comes from dynamical systems, from complex dynamics, but it's very much in the spirit of toric geometry. In toric geometry, you could start saying, consider a convex polytope, blah blah blah. So the vertex of the polytope, you could start like that. And here you start by giving these numbers that are going to define your dynamics, and some quotients of the dynamics are going to give this more or less. So you have this input data, that is the input parameters. As you vary these lambdas, you move in the modular space of these objects, and so when they are in this 97 case T1, looks a little like this. You have, say, 5 of these lambdas, and then you really ask them to be inside the origin, but not to be on the walls. As you cross the walls, you have the wall crossing, and but we're going to take one of these objects at a time first. And so then you have a dynamics, and then you define a manifold with those numbers. And the dynamic, there's a combinatoric symbol, just like as in geometry. You have some dynamics, and then there's some combinatorics that tell you you should omit these subspaces. Here the another is combinatoric that tells you should omit these subspaces, and then you have the dynamic, and then you take the quotient, and then you get the matrix. And so the only case in which it is Kähler, it's almost accidental, is when it's a torus. But if it is not a torus, it's not it's symplectic, and therefore not Kähler. But as Laura explained, they are not even in Fujiki class C. They're really far away from Kähler. They're really very much non-Kähler. So that's why some of the results that we're developing for these manifolds are quite surprising, because they are very non-Kähler. So the complex analytic properties of these manifolds are in the arithmetics of these numbers, the number theory of these numbers, the transcendental degrees and equations give you the complex parameter, and the topology given by the combinatorics, unsurprisingly. And then Loga proved in 2000 that when they are kind of simply connected, and the dimension of the space of rational affine relations among the lambdas, then the algebraic dimension is that. So really talking about this, what we're just saying. So in lambda, I was first to prove this, in spite of rumors, is that admits no constant neuromorphic functions generically, and when a lambda is that transcendental degree, that algebraic dimension, it carries a natural holomorphic collision of dimension n. And here it is useful to say it's somehow the manifold. It's something that feels a little bit funny at first. The manifold kind of knows its foliation, just knows its foliation, just knows what foliation it should have. So this is very interesting because it really then produces an equivalence of categories that I will mention in a minute. In any case, in 2004, Loga and Alberto proved that if you have this algebraic dimension, it's like saying that in the rational case, so to speak, then they foliate by complex tori in the rational case, and the quotient are the toric orbifolds, you know, a lot. So this is a way to produce the toric geometry. It's not the standard way in the textbooks to produce toric geometry, but it's a very good way to produce toric geometry. So you could say, well, definition of toric, or you could say definition of black. It could be an unusual one, but you could do that. But of course, it's very important that you're in the irrational case. Now, if you are in the irrational case, so rational case, you touch one of these points, so one of the points in the line sooner or later. But say that this ray manages to exactly evade all the lattice. It never touches an integral point. You're in the irrational case now. And now you cannot sensibly have a toric variety down here. What you have is a non-commutative space. It's a quantum toric variety. There was a quantum toric variety, just as a toric variety is made by tori. A quantum toric variety is made of quantum tori. So in the irrational case, you have this quantum toric varieties made of quantum tori glued together by the combinatorial instructions and the rate instructions of viewing from the fan, the quantum fan. That and then you need a little bit more information. You need to pick some sort of Planck length in every ray, at least, maybe a little bit. But at least on every ray, you need to choose what it means to be one. Here, it's very clear that you pick this one, you pick this one, but here you need to choose some Planck length. That will be literally a Planck length in some quantum integral system. So that, and now in 21, we published these results. In the non-rational case, the quotient stack is a quantum toric space stack. And there is kind of this correspondence between these ends and the quantum toric. And so they know that the fact that they know by knowing its symmetries, it knows its relations, it's kind of the same to have the quantum theory variety as it is to have the LVM manifold. So it's kind of a beautiful correspondence between these two things. So therefore, the forming LVM manifolds in the correct way will correspond to the forming quantum theory variants in the correct way. And so presumably, a possible path to explanation to some of the mysteries that we will be talking about, it's in the fact that the actual quantum toric stacks are Kähler in spite of the fact that the N is a very non-Kähler, secretly knows its symmetries, and there is this Kähler non-commutative space that controls a little bit what is that by the equivalence of categories, kind of controls what is going on upstairs. But this needs to be understood a little bit better by us.
We have a quantum variation of hot structure of quantum field map, whatever that means.
Well, we haven't written it down, but it's pretty clear what you would want to do for the quantum toric parameters because they are toric. It's not.
It's like the Laurent comment made at the end.
It is very much on that spirit. It is very, very much on that spirit. Absolutely, you are right. But of course, this needs to be developed. So welcome to the club. You really about these things. Even Rham and Rock needs to be written down more clearly. We know how you should go about it for years, but life is finite, so. So as you move lambda without breaking the diffeomorphism type is preserved. And now you consider a Gale diagram, a convex polytope, so that I generate a face of this if and only if 0 is here. So you have, it looks a total combinatorial geometry. So you produce a polytope that way. Of course, I'm not going to ask you to understand this combinatorial algorithm right now.
The wall crossing you were talking about.
I'm saying do not cross the wall. Then you will be in a safe place. The combinatorics will be fine and fixed. And but I'm not going to ask you to understand this algorithm. It's a computer algorithm that tells you how to go from one side to the other. So it tells you exactly how to produce. So, but here it is the situation. No? Here you have these two. I always get confused. Laura will tell me they are the indispensable ones. The red ones are the indispensable. Are the indispensable one? I don't know what the name is, but it's the indispensable ones. And so as you end up with a triangle for P, for the combinatorics of P, the polytope. Because this one is on this chamber. By the fact of being on this chamber, you end up with a triangle. Here, if you are on that chamber, you end up with a rectangle. And if you are on that chamber, you end up with a pentagon. So as you cross walls, here we cross walls, right? One crossing, another crossing. As you cross walls, you have these blow-ups, you have kind of blowing up things. And now we have this amazing blow-up minimal model program, super duper extraordinary machinery to understand all the blow-ups in this incredible Stern-Prokop tree, but that's another talk. The present zeta function and everything, all that kind of stuff. But for now, this is kind of the baby version. And in any case, Loa proves in 2000 P lambda is a simplicial polytope. Given any simplicial convex polytope, it can be realized this way. There's a lot of them, and the combinatorics is fascinating. Translations of the sphere. And given P and any k bigger than or equal to 1, there exists N with P lambda equals P and K or K plus 1 indispensable, given any K. So you can get everything you want on Earth. This has to do, of course, with also gerbs and things. In any case, simply connected correspond to K equals 0, 1. But there is a process of going from nk to n plus 2k plus 2. And n to n plus 1. keeping P the same commuters for P, adding two indispensable points. You can see it here. In any case, but now for complex geometry, this is mind blowing a little bit because topologically, this just takes this and multiplies by a bunch of elliptic curves. Topologically, just multiply by a bunch of elliptic curves. But the complex structures are not even related. As Laurent explains, you don't even have a resolved map from here to here. You don't even have a resolved map from there to there. Topologically, of course, yes. But not in terms of the complex structure. You get this plethora of non-Kähler complex structures all over the place by this procedure. And in analogy to homotopy theory, we call this procedure a stabilization procedure. And at some point, we get the stable range, just like in homotopy theory. At some point, we decide, we're in the stable range. And this concept that emerged from these questions is turning out to be a very interesting and useful idea or way of thinking about some of these things. As the homotopy type complement superspace arrangements, or as some topologies call them, this moment angle complex kind of related thing, but you don't need that really. Different terms are intersectional real ellipsoids, that's easy to see, or moment angle complex of the topologies. And then Bosio and Mercemont proved in 6 that they complete the homology ring, the homology ring over set. And there it is. You can see it's purely combinatorial. It's really about the geometric realizations of the combinatorics here. Almost it's beautiful for it. So simply connected case dominated the earlier literature. Many indispensable points seem like dispensable. Seem like the interesting case is the one where it doesn't have that kind of all those circles multiplied topologically. Nevertheless, complex analytically is a different story. But if K is bigger than M, then N lambda is a discrete quotient of an open set by a discrete infinite discrete group, a billion, of course. What else? Of diagonal matrix, hence a complex affinement. So we say that N lambda is in the stable range, and it is minimally stable if K equals N plus 1, and then so on and so forth. So for any simplicial polytope, there exists a minimally stable LVM and lambda, P lambda equals P, unique of to complex deformation. So you have this complex structure, but now you have all these magical complex structures that appear by the stabilization procedure, and they don't have these holomorphic maps anything. They are really all these spaces. So this is the anti-deformation talk. I cannot deform the one cross elliptic curve into that one cross an elliptic curve. I cannot do that. That I cannot do. It's a new complex structure. It's not the old one cross an elliptic curve. It's not that. So it's anti-deformation part. You cannot deform one into the other. They are really all new ones. And now the surprise, it's in our paper, published this year in Proceedings of the National Academy of Sciences, and we give a formula for the Hodge numbers of all these men. And the formula is striking in that it is as if it was a product with elliptic curves, but it's not. It's extremely surprising. What's more than that? As if you kind of let the formula talk to you, it tells you more and more. So far, you would say, that's it, let's wrap it up, let's go home, that's it. But no, it talks to you, tells you things. So let's see what it tells us. Anyway, when N is there was previous work, so we should be fair and mention this fact. We are being recorded. So when lambda is a torus bundle over a projective variety, the Borel spectral sequence describes the Dolbeault complex, Hopf and Ostinovsky. But Hodge numbers are a priori only upper semi-continuous in the non-Kähler setting. So you cannot compute this formula this way, not a priori. You cannot just say a continuity. So they are only a priori upper semi-continuous. Now we know they are extremely rigid, but you couldn't know this a priori. In general, Krutowski-Panov give a DTA model for the Dolbeault cohomology of n lambda, but it's very inexplicit, in my humble opinion. It's very inexplicit. So we follow a different strategy to do this computation. But anyway, the computation is there. So there is a combinatorial, again, it looks almost topological, but they are not Kähler, so they don't have this symmetry of the, I don't know what it's called, the symmetry of the Hodge numbers, you know. It counts pairs of non-adjacent vertices of the L-dom. More generally, for I vertices, let Pi be a maximal simplicial subcomplex with vertex I, then Pi has the homotopy type of a finite set of points, and that counts the BC of that. So it's beautifully combinatorial formula. And this echoes, this really is related, this really is very much like the topological formula. So you could have tried to guess the formula. This is not the way we came upon it, but once you have the formula, it starts talking to you. So that's true. So let me skip this part because we want to get, let me just say that polygonal minimally stable LVM manifolds satisfy the Hodge decomposition. It doesn't need to. It does. And more generally, a polygonal LVM manifold satisfies Hodge decomposition if and only if it is in the stable range. So this thing that started like in analogy, it's starting to exhibit that it's really a concept, it's really a thing. And the simply connected case is not there. It's just not there. It's just not there. So, nice. So, now I'm going to not show you this. I'm not going to flash through this, but somehow, once you have the numbers, you would want to have the Hodge-Levin polynomial, right? And the formula is complicated. You have all these combinatorial numbers. You're very smart, maybe you can do it, you know. But let's try not to be smart. It's always smart to not be smart. So let's just try to see what it's telling you. Again, you want to hear what it wants to tell you. And we'll come back to this. What it wants to tell you is that there is these hypergeometric functions in the background that allow you to go from these numbers to the formula you would want. So you use this bivariant formula. You can write in terms of hypergeometric functions. You don't need to write in terms of hypergeometric functions, but you can. You can. Why not? So you write in terms of hypergeometric functions. This is the combinatorics of this number. This is the number for the thing. I'm confused if I have a mistake on this formula or not, but it doesn't matter. And so we think very closer about two obvious, interesting examples. The stabilizations of the Hopf manifold, we would call quasi-Hopf, because they are not the Hopf manifold. They have these mysterious complex structures. These LVM manifolds that are the Hopf, topological, the Hopf manifold times copies of the curves. But the complex structure is this mysterious complex structure. And the stabilizations of the Calabi-Egg methods. And blah, 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 blah. But the whole point is that this is how you have the Hodge dynamic of the quasi-Hopf manifolds. So actually, this is the Hopf manifold, right? Yeah. And now you can produce all the quasi-Hopf manifolds by this beautiful Hodge-Pascal pyramid. I couldn't write it like a pyramid because it wouldn't fit. So I put the pyramid lying down, the Mexican pyramid lying down. And So whenever you have this window of 4, you add them up and you get this number. So in the classical Pascal triangle, not pyramid, whenever you have this window of 2, you get the one below. Here you get the one below, here at the center here, by adding the little 4. And as you move this window, you get all these numbers. And then you do it again, moving this window. And then you get all the Hodge diamonds of all the quasi-Hopf, even though they have these misfused complex structures. So you have this recursion formula. And this recursion formula, obviously, that's the recursion formula that was written in a silly fashion. But when you know the concept of the Hodge polynomials, and now it's motivated by trying to get combinatorics, trying to get generating functions for the combinatorics of the problem, you realize that what you are seeing, well, this is the formula. This is the formula. So you can actually write using the hypergeometric functions and simplifications, identical hypergeometric function, you can write the formula, the generating function for the numbers. And what you immediately realize is that you have the obvious recursion, where you multiply. So from the point of view of the Hodge polynomial, it is a product with elliptic curves. Again, very mysterious. So what's going on? So far you say, well, this is a little bit of algebra. Now I'm going to skip all this part where I do the hypergeometric function. I shouldn't, but I will. The story, because this should motivate the end of the talk, but whatever. You have to believe me now. So you have the properties of the Hodge-Delin polynomial. Observe that to prove the properties of the Hodge-Delin polynomial, it is quite striking. And when I say, they're very natural properties. But it was very surprising to me that to prove that you need the full force of the Lin's 3 Hodge theory papers. It was very surprising to me that to prove this simple statement, you need the full force of all these, the Lin statement. And part of the problem is that at some point, even if you start with a projective variety, but of course these properties are true for algebraic, but even true for Kähler methods. You could repeat the whole analysis by the Lin for Kähler methods. Originally it's for algebraic varieties. But of course, the problem is at some point you will take the difference of one variety by another. You will take the complement. And now you are in mixed Hodge structure territory. You are no longer, you need to have a good definition of what is the Hodge-Delin polynomial of this open field and so on and so forth. So you depend on compactifications and things like that. And now you are in this kind of, you are in the swamp. Now you have to fight to prove this kind of thing. So anyway, again, this is what I was saying. You have this kind of formula that is. I was very proud to get that formula in this very elegant fashion, in terms of just elliptic curves and this kind of funny polynomial 1 plus b, and nothing else. And then, but of course, you just multiply by an elliptic curve once at a time. But once you see the formula like this, it starts to be extremely tempting to do crazy stuff, There it is. You say, well, I really should consider this minus this. It's a nice polynomial to have. And it feels like the polynomial that generates a log transform, right? Now, of course, it doesn't have any symmetries or anything like that, it's just a thing. And then I will write these quotation marks here. And I will say, well, it's kind of important the difference between P1 cross E and H. And that's the quasi-Hopf. It was cross E from the point of view of the polynomial. But Hopf is not P1 cross E, obviously, otherwise it would look like an algebraic manifold, and it doesn't. So, but you start feeling that there are this kind of quotation mark objects, and of course, this thing within quotation mark doesn't make any sense. In the traditional relations for this tells you that this is a so-called Motivic measure from K0 bar. But you need this fact, you need this grammar of algebraic varieties, the fact that they are defined by equations, to be able to define K0 bar for non-Kähler manifolds, for complex manifolds. If you try to copy the construction of K0 bar, you get an incredibly interesting ring called Z, the integers, which doesn't have a lot of information. It's a very small ring if you do it for complex manifolds. For algebraic varieties, it's an extremely rich ring that contains, for example, the Lim polynomial, for example, as an archetypical Motivic measure. So, well, you start to feel this kind of this there, right? It's kind of there. And then, well, K0 bar is famously the ring of finite sums, as one from classes. And then there is this relation, x equals y plus x minus y. And then you have K0 bar, and then you have this theorem that depends all the way in HT3, all the way down to HT3. You can prove this. You cannot prove it before HT3. So it's kind of a mouthful to get here. And then there is no hope of having all that for complex manifolds. Absolutely no hope. There's absolutely no hope of having something like HT3 for complex manifolds. So what's going on? It's very confusing. It behaves as if we had that happening, but it cannot happen. So what's going on? Well, that's a Motivic measure. The universal Motivic measure in the polynomial ring into variables. The biggest morphism like that. Well, and then you start playing and say HM and like this. And then you have this difference, and it's really about this. It looks like the log transform is controlling the change in the polynomial. And you do all these calculations, and you do more calculations, and it really feels that you're working in K0 bar, but this is impossible because H is not in bar. The Hopf surface, non-algebraic. So what's going on? It's so confusing. Well, I will skip this part. That is very, very interesting, and we have developed a little bit more. Let's go back to the classical thing, the classical algebraic thing. The Hodge numbers satisfy the relations, the Serre duality, and the Hodge symmetry. But I didn't really know how to call it, but the Hodge symmetry. And then Koschik and Schreider showed that these are the only universal linear relations between Hodge numbers for all possible algebraic varieties. That is to say, the only ones that are satisfied for every compact Kähler manifold of dimension n. Nevertheless, in characteristic P, something funny is happening. They're constructed smooth projective varieties in characteristic P for which Hodge symmetry fails, 58. However, Serre duality, of course, still holds. Thus, the natural analog of the results of Koschik-Schreider is the following. The only universal linear relations between Hodge numbers of smooth proper varieties over a arbitrary field of character speaking are the ones given by Serre duality. That's it. In characteristic 0, Koschik and Schreider proved that the graded subrings given in degree n by the equations is a free algebra. And now this is algebra, this is algebra. Is HP1, H elliptic curve, and HP2, and that's it. And those generate all the universal linear relations on the Hodge polynomials of P1, elliptic curve, and P2. In characteristic P, Dolbeault proves, I made a mistake here, that you have to add a mysterious thing that has this property in characteristic. In characteristic 0, of course, it's just this, and this. And in characteristic P, you have this mystery. You have this S constructed by Serre in 53 that satisfies this. It's algebraic in characteristic P, but it looks like the Hopf surface. Like an LVM manifold. So, what is going on? Well, this is an important point, but let me skip it. Let me give you the punchline, let me just tell you what's going on. what's going on is that we have all minimal structures. We have this machine learning logic, mathematical logic, that separates a kind of complex geometry that is bigger than algebraic geometry, contains algebraic geometry, contains scalar geometry, but contains many all LVM manifolds, for example, many non-Kähler manifolds, and it's called definable geometry over an all minimal structure. And the theory of minimal structures tells you that they are classified, and then you have the very famous theorem that tells you surprise exponential functions there, and all this story, beautiful story in mathematical logic from the late 80s, early 90s, throughout the 70s, late 80s. And it was kind of conjectured somehow by, quasi-conjectured by Grothendieck. He, in these letters that he wrote, would write it moderated geometry. He would say this kind of this geometry that is complex geometry, it's not algebraic geometry, but it's controlled and it doesn't have this pathology. But to say this well was the tour de force in mathematical logic, with some extremely beautiful theorems, a couple of them in mathematical logic, that said, yes, this geometry exists. And it's called definable geometry. And that solves a little bit our mystery. We have every complex manifold, by the way, Kähler or non-Kähler, is definable. Compacity implies definability. So well, that helps. And now we have this remarkable theorem. Let me try to say. There is a theorem of Bittner in 2004, and she proved something amazing, beautiful. She proved that if you take K0 bar, the thing I defined, it's generated by projective algebraic variables with the blow-up relation. And that is the same ring. If you generate it with projective algebraic variables, the Bittner ring is isomorphic and equal to K0 bar. The same ring, isomorphic to K0 bar. It's the Bittner theorem. And now we proved, and this is in our paper, Bittner's theorem in the definable world. But now it's mind-blowing, right? Because you say, on the left-hand side of this theorem is compact complex manifolds and the blow-up relation. No mathematical logic. On the right-hand side of this theorem is all about mathematical logic. It's K0 F. And we prove that they are isomorphic. That K0 F is exactly equal to the Bittner ring of compact complex manifolds. To me, it was absolutely striking that one side doesn't talk at all about mathematical logic, and the other side is all about mathematical logic. So it's very striking, but true. And you can prove a little bit more. In the classical case, if you have K0 bar, this would be stably birational classes of varieties. And now we have stably bimeromorphic classes of complex manifolds. So this, of course, this is a very famous relation between birational geometry and the Motivic ring. And we have it in this complex geometry setting with larger than lots. Dolbeault cohomology defines a Motivic, and this is kind of a surprising theorem because now we do not have Hodge theory 3. Nevertheless, with results of Hironaka, the school of Hironaka, I should know the names, I apologize, and Brosnan and other people, we can prove that nevertheless we have a Motivic measure. Using kind of visual theorem kind of estimates. And well, the log transforms talks about this very interesting phenomenon of phantom-like behavior. And now we have the theorem. H is missing. Now we have the theorem just like the characteristic P theorem. Now it's true for the definable words. It's identical not to the algebraic varieties case, so we will come to characteristic theorem. It's identical to the characteristic P theorem. This is likely mysterious and needs to be understood better. Well, and then I wanted to talk about why there is this beautiful hypergeometric D modules on the Motivic ring. But let me not do that. Thank you very much.